So this video is for the chi-squared goodness of fit test. So here we have an example. Company claims that a certain bag of candies produces the following distribution of red, green, and yellow. So we could set up a table, red, green, yellow. Okay, and then we've got observed frequencies and expected frequencies. And so that's what we were just given, the expected frequencies, but we can't enter those. Goodness of fit test doesn't want percents in the table of values. So this is going to be L1, L2. We should also set up our null hypothesis in a goodness of fit test would be that the given distribution is correct. So given distribution is correct, or that, in other words, we could say the observed frequencies are not significantly different from the expected frequencies. Okay, and so then this would just be the opposite. Given distribution is incorrect. This is more in context of the candies, but in general, for our alternative hypothesis, we're just saying the observed frequencies are significantly different than what we would have expected. So now we have to figure out, sometimes it tells you the total amount, but here we just add 63 plus 72 plus 65 and we get 200. So now when we calculate our observed frequencies are already given. We can put those in the table as is. But our expected frequencies we have to calculate. 25% of 200, 25, we actually have to calculate that and put that number in our table, or you can type in the calculation. So I'll just put that. So for green, we want 40% of 200. For yellow, we want 35% of 200. So now I can pull up a calculator and just go to stat, edit, put in the observed frequencies for L1, and then L2, I can calculate these right on the list. So 0.25 times 200 is 50, and 0.4 times 200 is 80, and 0.35 is 200. A common mistake would be to enter in the percentages, but you'll know that's wrong because when you go to stat tests and the goodness of fit test, it would tell you that you made an error. So we want our observed in L1, expected L2. You can flip those if you want, but typically observed is first in the test. So just make that L1. Degrees of freedom. In order to do this, we just take the number of our candies and subtract 1. So that's going to be 2 degrees of freedom. Goodness of fit test is always just going to be 2 lists. It's not a matrix. The matrix is only used for independence test. So now we calculate, and there's our values. So chi-squared value, the p-value is what we really want, 0.103 to 3 sig figs, and we want to compare that to the significance level. So since this is greater than 0.05, we fail to reject. So we're basically accepting the null hypothesis that the given distribution is correct. There's no significant difference between observed and expected frequencies. If the p-value would have been less than 0.05, one thing we might want to watch out for is if there's scientific notation, like if it says e to the minus something, that would mean our p-value actually was smaller than 0.05. And then we would reject the null and say this distribution doesn't meet. These frequencies are significantly different from each other. But in this case, we do have a p-value that's greater than the significance. So we fail to reject, which is kind of like accepting the null hypothesis, and we just say, really we should say there isn't enough evidence to suggest that these expected frequencies are different from the observed.